Hello, welcome back. There is a huge gap in my lecture series. Last time I think we covered quite a few subtopics in work and energy. Probably I discussed the combination of your friction, gravity, the chain problems, spring problems, and I combined most of them and then tried to do. Now we go a little deep into that. For example, work and energy, we combine this with the conservation of linear momentum. I am not going to discuss the conservation of linear momentum separately, but in the process I'm going to do collisions. It's also part of your work and energy you should understand. Right. Now, collisions. Now this is important. Whenever two bodies come under the influence of each other, collision is said to have taken place. This is why I am writing this also. I am telling you because the problem is the textbook definitions are different always. Whenever two bodies come under the influence of each other, collision is said to have taken place with or without physical contact. This is called a collision. Very important. I can surely give you an example. Simple, along a line, you take 2 point masses, now let them move and then collide. That is fine. They collide and then probably they will move together, they will go back their respective directions and whatever. If you take a carrom board, you take a striker and try to strike a coin, now there is a way that it will go beyond your imagination, it will go into the hole that is meant for it. Or sometimes we play in such a way that the board coin itself will jump out. So we are giving a example of collision of 3D. If you have it on a line, we call it as 1D collision. And if you have it in a plane, we call it as a 2D collision. And if it is in space, then it is a 3D collision. Fine. In all these cases, you are seeing that the bodies are actually undergoing physical contact and you are able to hear the sound as well. Now, on the other hand, I have a powerful magnet, say South Pole on this side. You know very well that it has its own zone of influence. From somewhere, you don't get a unipolar thing. But if I throw it like this, say from here, now if you throw it, it will come and then go like this. Collision is said to have taken place. There is no physical contact. It's very important. Physical contact is not necessary for a collision. And it has got serious, several consequences. I'll tell you one by one afterwards, not at this moment. But you should understand. So, for a collision to take place, it's enough if the two bodies come under the influence of each other. Then the collision is said to have taken place. There is no sound generated here, nothing. And I am going to discuss what is the consequence of sound not being generated. Not being generated. Now this is very crucial. Okay? So this is about a general collision. Okay? Physical contact I have already explained, and most of the subatomic collisions or atomic collisions generally are considered to be without physical contact, and you don't come across the The collision doesn't lead you to any sound. Okay? Fine. So, I can categorize collisions into different types. Say, for example, 1D collision. Collision along a line. This is collision along a line. 2D collision. Collision in a plane. Carrom board. 3D collision. Roadside accidents. A scooter coming like this, another scooter coming, hitting and then going up, etc. So 3D collision. Collision in space. 3D space. These are called 1D. I'll explain one by one. Mostly you have 1D collision in your syllabus because 2D collision also will come in. We will discuss that as well. Okay? So this is fine. This is so far so good. There is another categorization which is very important. Very important. One, elastic collision. Semi-elastic collision. Inelastic or perfectly inelastic collision. Very crucial for us. These definitions I will tell you one by one. But two types of those things you should have in your mind. 1D collision. You have these three in all the 1D collision cases, 2D collision cases, and 3D collision cases also are got in all the three categories. Okay. Now, whenever you see that, for example, two bodies have come into contact with each other, they collided. You know, generally what happens is, this collision takes place for a fraction of a second. Very, very small interval. Say dt. Say dt. Very important. And suddenly you have a ball goes and hits it. Collision has taken place there. Or a ball is coming, you are catching it either abruptly or slowly, whichever way you like. Now suddenly what are you trying to do? You are changing the course of movement of the body. When you say the course of movement of the body, I am talking of linear momentum change. There is a linear momentum with which the body is coming. If you are stopping it, you are making it change. If you are putting it like this and hits and goes, you are changing the direction, therefore you are changing the momentum. In either case, you are changing the momentum. But when this takes place abruptly, there is an impulsive reaction. For example, a bowler bowls and the batsman hits it. The interaction between the ball and the bat is for a very fraction of a second, very, very small interval of time. But impact took place. The impact took place. There is an impulsive action. There is an impulsive action. See, if I have a bat, I keep on holding the ball and take it, there is no impulsive force act. Continuous force is acting. But if I hit it and leave it, impulsive act. I have thrown a body. I have given impulse to the body. Now look at the language I am changing. I have applied an impulsive force because of which impulse is given, because of impulse momentum is taken. Hope you are following that. I am now using an impulsive action. An impulsive force I am applying on a ball, throwing the ball. What was the initial momentum of the ball? 0. I have applied impulsive force. Therefore, I have given impulse to the body, and because of impulse, its momentum has changed. So, there is an intimate connection between impulsive force, impulse, and linear momentum. You get this point? I hope you have understood this. Suppose if I take an impulsive force and apply it for a very small interval of time, so this impulsive force need not be a constant. So, if I look at the total interval, 0 to t, what is the impact of all this? This is what I define as the impulse. This is impulsive force. This is impulsive force. That means any force acting for a short duration is called impulsive force. So, how does this impulse? It's very difficult to talk about the variation of this force. If I really plot it, when the ball comes and holding on to the ball, and you think, sir, I've just caught the ball. But what you don't understand is that you have taken such a time, that maybe a microsecond, 100 microseconds, milliseconds, I do not know. But yes, you have taken such a time, and during this time interval, you are thinking that the force is constant. No. If you really plot that, you get a surprisingly, look at this, with the time I am plotting. So this is 0, this is delta t. This is very typical variation, difficult to understand the variation, very complicated variation. It doesn't follow normal distribution, it doesn't follow any skew distribution, nothing. In fact, the exchange has taken place even in this delta t. In a very short interval of time, the exchange takes place. I mean, this is very, very important. Two balls come, collide, and then go back, let us say. You think you are looking at only ball hitting, going back. But during that, the exchange that is taking place, the impact that is happening in a very, very short, fine interval of time. Micro level. We may not be concerned with that. But then, if I take that and find out what is that impulse, impulse by definition is the product of impulsive force and the time interval. Since it is a variable force, I am taking integral. This is called impulse. All forces, you don't know what kind of forces are they, right? You have 0 to t. But then I know what is sigma Fi, ma dt, mass constant, and what is this? dV by dt. And what is this? M dV, initial, final. Well, ultimately, you are saying impulse results in change in momentum of the body during that time interval, but never give that as the definition of impulse. Definition of impulse is this only. Okay? But the consequence of impulse is change in momentum. This is called impulse momentum theorem. Impulse momentum theorem. So far, so good. Whenever there is an impulse, yes, I can find out. But Now comes a very, very crucial question. Very crucial question. Before I give you that concept, I'll help you with an example. I'm dropping a ball. It will hit and come up. Agree? But so, no issue. But I'm throwing the ball like this. It will go. Okay? Angle you increase. It will go. Increase, increase, increase. Now finally on its surface, I throw a ball. What happened? No impact took place.
Amma?
No impact took place. No impact. That means when I am dropping the ball vertically down, it is hitting and going up. Then complete maximum impact took place. When I do it parallelly, no impact took place. That means maximum impact, less impact, still less impact, much less impact, zero impact. Could you understand? We know that is practical. Very important point. Very important point. The line along which the maximum, that the impact takes place is called line of impulse. The line along which, in which direction the impact takes place is called line of impulse or line of impact. For example, when two bodies collide, draw a common tangent. If it is a curved surface, draw a common tangent. The tangent is along which no impact takes place. This is called common tangent. Whenever two bodies undergo a collision, at the point of contact, at the point of contact, POC, point of contact, draw a common tangent. Along which you are sure no change will take place. If the body has certain momentum in that direction, the same momentum remains. If the body has certain velocity, same velocity. I am talking of just before the impact, just after the impact, or just before the collision, just after the collision. Okay? Likewise, I am creating. Okay? I hope you have got this point. First of all, you have to identify which is common tangent, perpendicular to common tangent, perpendicular to common tangent, line is called line of impulse or line of impact. Line of impact. Line of impact. It's called line of impulse or line of impact. Very, very important. I do not know how to describe this because if people understand this, the collision problems are absolutely easy to solve. I want you to understand that. Now I'll tell you. One-day collision. It's moving like this, it's moving like this. Where they collide is one-day collision? Obviously, The line of motion itself is the line of impact. In 1D collision, line of motion is line of impulse. Okay, but not in 2D. In 2D, this is a plane. Body comes here, another body comes here. This is common tangent. Normal to this is line of impulse, J. Likewise, you have to, every time there is a 2D problem, every time collision means first thing draw common tangent, at least intuitively, and then draw common that line of impulse perpendicular to that at the point of impact and at the point of contact. Okay? Now, that will give you line of impulse. What is the significance of line of impulse? Now, common tangent, no change in momentum. Line of impulse, impact takes place, and all changes take place along the line of impulse. What changes we will discuss. So common tangent is okay. Now, let us say two bodies undergoing collision. Body is moving with an initial velocity u1, another is moving with u2, and just after, let it collide for delta t. After collision, let the velocities become v1 and v2. Okay? Let the line of impulse be along j cap. You know, j is a line of impulse, j is a vector number, j cap is unit vector. Now, I want to know relative velocity of approach along j. I say u1 minus u2 along means j cap. Relative velocity j before collision. The relative velocity of separation along j after collision. V1 one is approach, other is separation. So negatives. Two bodies undergoing collision, moving with u1 bar, u2 bar, it is with two dimensional, I don't know, three dimensional, I am not worried. u1 bar, u2 bar. Immediately just before collision their velocities are u1, u2. Just after collision their velocities are v1, v2. And if I take the velocity of approach, relative velocity of approach with 1 minus 2, then separation must be 2 minus 1 because these two must be taken in the opposite direction. So I put negative sign here. If I take a ratio of the two, then I call it as E, coefficient of restitution. This is a very, very important concept in collision. It is called coefficient of restitution. Restitution means retrievability. Retrievability. How effectively the bodies can retrieve their momenta. How effectively the bodies can retrieve their momenta. Maximum literally is 100%. That means E is 1 means 10% retrievability. 0. You can't retrieve anything. That is the meaning. Okay? That means coefficient of restitution varies between 0 to 1 and always positive because one is approach, other is separation. If both would have been approaches as per definition, you could have got a negative value of coefficient of restitution. To make it positive only, they have given one is approach, other is separation. So if you take one positive, other must be negative, you already took. How do you write that? I am writing it again. So sorry. Remember, I don't know whether I gave it wrongly. Be careful. I'm sure I gave it wrongly before. Separation divided by approach. Go back and correct your thing. It is separation along this divided by approach along that. Along that means what? Line of impact. This is correct. The previous one probably I gave U above and V below. No. The final must be above and the initial must be below. Okay? This is the definition of coefficient. How to write the definition of coefficient of restitution? The ratio of relative velocity of separation along the line of impulse at the point of contact and the relative velocity of approach. Separation just after collision. This is relative velocity of approach just before collision. Along the line of impulse at the point of contact. This is the definition of coefficient of restitution. I want every one of you to go through it carefully and then put it. This is important. E varies between 0 to 1. Can't be negative. They can never be negative its value, and it's very, very crucial. Okay? The line of impact and the line of the impulse and the common tangent. Okay? I hope this is noted. How to get this, I will tell you. But one important thing is, in all collisions, linear momentum of the system is conserved. Because all forces are internal, no external force. So I think probably I've already talked about this long back. The body is moving with the U1, mass M1, another body moving with mass M2, U1, V1, M2, V2, this is before collision, after collision, let them undergo for a time interval delta t. Then the total initial momentum is M1 U1 plus M2 U1. The total final momentum is M1 V1 plus M2 V2. Okay? This one. And right. So, impact, what is the force by body number 1 on body number 2? On body number 2, it is M2 E2 minus M2 E2. It is moving with U2, that change to E2. Body F21, M1 V1. One is action, other is reaction, because both are simultaneous and internal forces. So therefore, that implies this is Pi, this is Pi. Therefore, the total linear momentum of the system remains constant in any type of collision. That is universal. You have to remember, it is a universal phenomenon. Not so with kinetic energy, not so with potential energy, not necessarily with mechanical energy. Yeah, total energy, of course, it is always conserved. Let us not get into that. So, one important thing is, linear momentum is conserved in all collisions. 1D, 2D, 3D, elastic, semi-elastic, inelastic, all kinds of collisions it is very important. Based on this, I'm now going to categorize these things. Elastic collision, semi-elastic collision, inelastic collision. I think, let me tell you, E, this is 1, this is less than 1, but greater than 0, and this is 0. This is the definition, you said it. P, linear momentum. Now there is a problem here. Whenever I am talking of something, what am I talking? There are 3 phase stages you can see. Just before, just after, during. Just before, just after, during. Just before collision, no, momentum is conserved all the time. Momentum is conserved all the time. C for conserved. I am taking 3 aspects, 3 stages. Just after, just before, during, just after collision. Okay? Fine. Linear momentum is conserved in all the stages. Kinetic energy, very important. Imagine 2 identical bodies, point masses, come and collide. There is a chance that they will go back. So, I said kinetic energy is same after the collision, before the collision is same. But during the collision, when these 2 come and collide, obviously they must have come to rest. They must have come to rest. The whole of Ke might be converted to potential energy. Might be converted to potential energy. In the case of elastic collision, we define even, not only that, kinetic energy just before and just after is same, but not during. During, kinetic energy is not conserved. Not necessarily. In many cases, it's not conserved at all. So, kinetic energy just before and just after conserved, but not conserved. Here, oh, you are able to distinguish this. During, as the impact takes place, at one instant of time, there is a very chance that the kinetic energy could become zero or less. Same is the case with potential energy. Not conserved. But mechanical energy. Mechanical energy is conserved in all the three phases, in elastic. But here, mechanical energy total energy, without any doubt, that means thermal, sound, electrical, all forms of energy that remains constant. So be careful when I have distinguished all this. It's very, very important. E is most crucial. 1 less than 1 greater than 0 equal to 0. Kinetic energy, people say elastic collision is conserved, is not correct. During elastic collision, kinetic energy will not remain the same as just before collision or just after collision. You have to be very, very careful in this concept. Language is important. Okay? So you have it. Fine. Kinetic energy is not conserved. Potential energy is also not conserved. And I have given that. But total energy, be it sound, be it thermal, be it mechanical, total is bound to be conserved in all these cases. Is it okay? Right. Let me put a